Hello everyone, my name is Will Blair. I'm a PhD candidate at Boston University. Today I'll be discussing microservice-aware reference monitoring through hybrid program analysis. This work has been done in collaboration with members of the Cybersecurity Intelligence team at IBM Research, and I'd like to take a moment to acknowledge our sponsors and emphasize that the opinions given in this talk are those of the authors and not necessarily those of the Department of Defense or the US government. Now, to motivate reference monitoring, let's go back to 1973. When a young science fiction writer by the name of Michael Crichton introduced the public to the concept of a computer virus as a small program that replicated itself across a series of androids, causing them to become malicious and hunt down the human guests of a theme park. Fortunately for us, nobody has actually attempted to implement such a park, but if they did, we have some pretty solid solutions in place for reference monitoring the individual end hosts that would power each android. In this setting, if an adversary or piece of malware were to compromise an individual process and start issuing system calls, a reference monitor could intercept these system calls by applying the policies authored by individual analysts that restricted individual processes' ability to affect system resources or disclose sensitive information. Now, the state-of-the-art tools that we have today, such as SELinux, AppArmor, and Audit, allow authors to write stateless security policies, and new advances such as the Common Intermediate Language for SELinux allow a higher level of abstraction to more easily author these policies. Unfortunately, though, implementing quality security policies is still a time-consuming task and requires a significant amount of domain expertise to do correctly. Furthermore, these days, individual applications don't consist of a single end host. Indeed, a large distributed application often uses enormous amounts of cloud resources and itself is implemented as many different pieces within a microservice architecture, which consists of many different communicating containers that run across multiple computing nodes. In this case, let's consider the orchestration framework called Kubernetes. And imagine if an adversary were to compromise a particular container. They could, of course, disclose sensitive information, compromise, but if they escape the container abstraction on a physical node, they could compromise the entire node, or go a step further and compromise other resources located on the cloud. This demonstrates that cloud operators take on a significant amount of risk by running code on behalf of their customers. And furthermore, they can't always guarantee that their customers are going to write high-quality security policies to keep their applications secure from exploits. Furthermore, as programs change, they can't rely on their customers to keep their policies up to date either. For this reason, we want to propose a microservice-aware reference monitor that works in the following way. Suppose that we take as input the Docker image that powers any containerized application used. We extract its entry point, represented as a executable linkable format program or a native executable. We micro-execute that program in an analysis framework in order to automatically generate a security policy that encodes all the valid sequences of system calls we would expect to see during any execution on our cloud platform. Next, we take that Docker image and we allow it to run within a physical computing node. And over its lifetime as a container, an adversary may exploit it, at which point the offending system calls would appear in lightweight system call telemetry provided by SysFlow. Now, once the Microservice-Aware Reference Monitor, or MRM, is co-located with the protected program, it now has a policy and a trace, and it wants to see whether or not the trace inhabits the given policy. Or put another way, as an exploit occurs, we want to observe that that trace deviates from the policy that we inferred in our first stage and raise an alert to an analyst, or possibly take more drastic measures and terminate the exploited container in response. Now, some research challenges that we encounter in this endeavor are first modeling external libraries, since analyzing both the application and all of its external library dependencies may be infeasible in practice, and also accurately recovering system call arguments in the presence of programs that receive user input, scaling this analysis so that it can actually be useful on real workloads, and then finally efficiently enforcing the models that we generate at the computing edge so as to not interfere with the normal operation of the applications that we're responsible for running. So with that high-level view, let's introduce the binary analysis platform, which powers our analysis. The Binary Analysis Platform, or BAP, has been developed over the last decade at CMU, and at a high level, it takes an individual native executable program P as input and lifts it into the analysis platform, first as an intermediate language IL, which preserves the semantics of the underlying instruction set architecture, but also maintains a second representation of the program in SSA form. Now, at this current point, you can implement static analyses, which may resemble, say, an LLVM compiler pass that allows you to scan over the instructions and perform different analyses over the application itself. But the killer app for our purposes is the Primus machine that is also implemented inside recent versions of BAP. Primus is really cool because it allows you to take the program in its intermediate language representation and feed it to a Primus machine that can execute arbitrary segments of this program starting from any possible point. In our case, though, this is a framework that has a tremendous amount of features, but for our purposes, you can imagine we're just using this machine for the purpose of executing arbitrary code found inside our program. But the execution and control of the machine is completely up to the analysts, the analysis being run on the particular program. Now, if we were to simply just micro-execute a snippet of code, the machine maintains its own process abstraction of a process address space in a corresponding stack and heap. And also for external dependencies that a program may call out to, it maintains a Lisp interpreter that allows an analyst to stub out the functionality of library functions without having to micro-execute them directly or provide equivalent implementations for them. As an example, if I were micro-executing a little program that required network functionality, it's much easier for me to go to the Lisp interpreter and state that any call to bind should just return 0 to support the normal execution of the program, instead of delving into the libc, trying to micro-execute the corresponding implementation of bind, and therefore slowing down the analysis if I'm not concerned about the implementation at bind. Well, in this example where we just simply stub out a specific function with so that it returns a fixed value is a simple use of the Lisp interpreter. The framework that you have at your disposal is very rich. You can modify using that Lisp almost any part of the Primus machine without the need to compile new code. Furthermore, you can also call back to your OCaml plugin if you want to utilize functionality found there, such as if you want to utilize some OCaml library in your stubbed code rather than implementing everything inside Lisp. So with this framework in mind, how can we synthesize policies for arbitrary programs? Well, at the very beginning, we start off by micro-executing a given program P inside Primus, and we make all of the files that are stored inside the program's Docker image available to micro-execution. So if a program reaches for a configuration file at the beginning of its execution, Primus will reach out to the corresponding file found inside the layered file system that makes up the Docker image and ensure that the program has access to it. Now, while it's micro-executing, our plugin maintains this abstraction called a behavior graph, where you can imagine the root of this graph is identified by the binary program that we're analyzing. In this case, imagine we're polling some database file that's stored on disk. And while micro-executing this program, we observe a read at a specific term X inside the intermediate representation of the program. Think of X as a specific point in the lifted representation of the program. And then later on during micro-execution, we observe a write system call at a different term. The way this behavior graph is built up is we add nodes for every single term that calls a system call, and then the edge that points to those nodes it represents the system call that was made. So if this simple program simply reads and writes repeatedly, we will later on encounter a term X again when we read from the corresponding configuration file for this database and continue on doing this in the loop. Now, what would be the security policy for this program, a program that has this behavior graph? Well, it's for the MRM, we're not terribly concerned about which point inside the program a particular system call happens. What we're interested in is the resources that the system call acts on. So when we generate a policy for this particular program, we'll replace the term inside every single node with the arguments that were passed to the corresponding system call that was made at that term. In this case, if the db poll simply read from a file stored inside the var folder and wrote back to it, the corresponding policy would encode that this program, for all executions, can only read and write in sequence to the same file on the disk. And reading and writing to any other file should yield a security violation. So the overall output of our policy synthesis is a type that can be assigned to the program P that represents all the side effects or system call sequences that we could expect to see during its execution. So now with this ability to generate policies for an individual program, how can we deploy the MRM at the computing edge in practice? Well, we start off with a Kubernetes node, and we allow each individual workload to run in its own pod. Now, we store our MRM inside its own daemon set that has access to the system call telemetry produced by SysFlow, and the MRM has a corresponding policy for each individual workload given inside the node. And if an adversary is able to exploit a particular program, it will notice a deviation in the corresponding model or policy. If a deviation has occurred, or we observe some record inside our system call telemetry that deviates from a model, we can raise an alert to an operator or terminate the workload in response. So how is this implemented in terms of the configuring SysFlow and then actually implementing a SysFlow processor, which we saw an example of in the previous talk. First thing we want to do when we configure the SysFlow pipelines to support an MRM is to define the path of records from the telemetry source all the way to the exporter, or the entity that will then consume the output of the MRM. The MRM's job is to identify alerts or identify records that deviate from the policies generated by BAP. So what we can do is we just establish a straightforward pipeline from the telemetry source to a flattener to the MRM. The MRM also draws from policies produced by BAP in order to provide it with the models of what behavior it can expect during a program's execution. And then any deviation, the records that come out of the MRM, represent those records or a signal that a possible intrusion has occurred. Now with this configuration in place, the SysFlow will now emit records to our MRM, and the MRM itself sits between the collector and the exporter inside the SF processor. So instead of, in the previous talk we saw the policy engine sitting in this place, we now have an MRM sitting in the same location that reads in all of the records produced by SysFlow. It maintains finite state machines for each individual thread observed inside the system call telemetry, and it continuously checks whether or not the records produced by the system call telemetry can conform, or it can execute the finite state machines faithfully, or if they deviate at all from the models given that are stored along with the FSMs. Any event that that is not expressed inside these finite state machines yields an alert that is then passed off to the exporter. So how do we evaluate the effectiveness of an MRM? Well, the DARPA Cyber Grand Challenge dataset provides a corpus of challenges, all of which that utilize a very simplified system call interface to a customized CGC kernel. This is useful because it limits the expressiveness of policies that we need to support for our prototype implementation. And it also comes with a corpus of inputs that exercise the full functionality of every challenge contained inside the CGC dataset, in addition to a corpus of inputs that demonstrate the presence of vulnerability in each challenge. So what we can do is wrap each challenge inside a Docker image, make it so that SysFlow traces its execution, and then feeds every record into our MRM. and we ensure that every single trace produced by benign inputs correctly inhabits the policy that we've generated for a given challenge, and that the corresponding proof of vulnerability inputs lead to a violation, or that the policy does not type check under a given trace. So with that in mind, let's go over a simple demo challenge that offers a simple text-based game to a user. It has a relatively simple behavior model. It simply maps some memory for game state and then reads and writes from the user input to implement the functionality of the game. So the thing that we've set up here is that our analysis runs behind xinetd so that we can run the CGC framework to apply the inputs given in the CGC dataset automatically. And what you're seeing here is the interaction between the CGC's test framework and our analysis system as it builds up the model. So the model that we've just generated can be shown here. This is the graph.is representation. The other representation is a JSON object that encodes the behavior graph that is then, or the finite state machine that is passed off to the MRM to be enforced at runtime. And if we take a look at how the MRM actually behaves in runtime, we can take a look at how the FSM processes the SysFlow traces over benign input. So one that simply just plays the game normally. Without going into too much detail, all that's happening here is that the MRM confirms that given the capabilities expressed that it observes at runtime in the SysFlow traces, namely the alternating reads and writes to a specific port, that allows it to explore all the functionality of the FSM, and no events given inside the trace deviate from the FSM. And it then exits normally as the model predicts. However, in the malicious case, where the user successfully crashes the program, we get a record is flagged as problematic as output by the MRM because an exit that returns with a status code indicating a segmentation violation is not expressed within this model. What the MRM does is it observes that an exit event occurs in the SysFlow trace and that the return value of 135 does not conform to the expected value of 0, and the MRM generates an alert in the form of a SysFlow record for an operator to examine. So that's the demo of the Microservice-Aware reference monitor. And with that, I thank you for your attention. I'd be happy to take any questions that you have. Thank you.
And now I'd like to welcome in William. William, thank you for sharing your work and joining us here for the live Q&A.
Thank you for having me here.
All right, let's get to your first question, and that is, how would you compare your experience working with BAP/Primus to other analysis tools like Ghidra?
Well, to answer that, I think go back to when I presented my idea at IBM Research's kind of intern event during my first internship. I got to talk with a guy that does CTF on CMU's CTF team, and he had worked on the DARPA CGC project and had quite good experience with BAP and Primus. And I asked him, "Oh, is BAP good for CTF then?" He said, "No, I just use IDAPRO or Ghidra." And what I kind of took away from that, and in drawing from my own experience of using analysis tools like Ghidra, is that they're really good for gaining human insight into looking at programs or doing this kind of manual-driven analysis. I know that tools like those have rich programming environments to analyze the given, say, program under analysis in order to automate some of the analysis tasks that you have during your workflow. But what I really like about BAP and Primus is this like rich programming environment to not only say, analyze a given binary by implementing, say, analysis passes that are akin to what you have for doing compiler passes in the LLVM framework, but also to like alter the program and then execute it in any way that you see fit. But I mean, the simplest analysis you could start off, or a hello world analysis with BAP, is just say computing histograms of the different kinds of instructions that you find over a given binary. So you can plot out, say, how many adds or subtracts or how many loads or stores are done in a given program. But the real power that or use or way that I saw AppArmor shine as I'm doing this work is the ability to not only emulate but alter the given program and then execute it in arbitrary ways using that micro-execution technique that was developed at Microsoft Research. So instead of kind of just bringing up a program for an analyst to do some work, what's really cool here is I got to use it in order to automatically try to build a behavior profile or a security policy from a binary without having to without involving a human analyst in that process.
Thank you very much for that. Next, from a question coming in from Discord asking, for working with lightweight devices at the edge, how much work have you been able to do to gather data as rich as possible and as small packages as possible?
Well, for that question, I've been very lucky in that I myself haven't had to do a significant amount of work in gathering the data at the computing edge. I've got to build off the work that Fred and Terrell have done in developing SysFlow, such that my little plugin that implements the Microservice-Aware reference monitor just gets, it sits after the flattener component in that diagram that was given in my talk, and it just consumes these lightweight records within flows instead of having to actually perform this compression over a large volume of system calls that you'd see coming out of, say, a container that's sitting at the computing edge in an individual Kubernetes node.
And what is the interaction with developers during development, if any?
So that use case hasn't been ironed out completely yet because I'm just doing this work on my own. But what we kind of envision, or the vision I have in my mind is, the way developers deploy code these days is they containerize everything and they ship it off into running containers, right? And as a cloud operator, you have access to the data that's being fed into those programs as input during production, and you can monitor it in real time using this the SysFlow plugin that can run alongside the given workflow. So the way you could build up these the models kind of over time is have users potentially opt in for the ability to construct models in a kind of overnight processing. So as people build their products in a CI/CD pipeline, you could imagine you have this analysis process that runs asynchronously to development that gradually builds security policies for developers. Now, of course, that the claiming that you're going to be able to build a security policy for large binary applications automatically may be a little far-fetched. And for that reason, bringing in the developers to potentially add insights to the analysis would be a helpful thing to do to actually make the use case useful.
Right. Now we're going to move on to a question from Ronaldo asking, any thoughts on metrics about how often there are false events? Yeah, the rise of false positives would be a problem in this because as you can imagine, the having alert fatigue for an MRM would probably limit the usefulness, right, would limit the probability someone actually would use it in practice. The approach that we're taking for that is for limiting or how sensitive it is to the MRM to false positive is trying to build this analogy to type systems, right, where the security policy that you build for a given program represents its type or encodes the kind of side effects that it may issue during its life, any given execution. And you'd want to strike a balance between being overly precise in that model, namely saying, for instance, if this program reads from a file, if during your analysis you see that it reads from, say, one specific file that's contained in the container image, you have pretty good confidence that that read within that model is going to only be to that specific file. But if you have something coming in from user input and you, say, restrict that activity based on one specific input that you've seen, let's say, while you're building your analysis, right there's a potential source for false positives, right? Because you have, let's say, your model is built on one user input, and when somebody else comes along and gives slightly different input, you could yield a false positive, right? Because maybe an argument to a system call would be derived by user input. So trying to strike this balance between, let's say, maybe introducing some, I've thought about some symbolic variables within the policies to permit that flexibility would be how I would try to limit false positives like that. But for cases where,
you just observe the binary given access to the file system that's given on the container image. You see the program always reach for, say, a configuration file, or always work on some specific files that are given inside that container image. That'd be, that seems like a really strong signal for restricting the policy to just those files on the file system.
Okay, another question from Zoom asking, you talked about stubbing out calls to external services. Does that have to be done manually, or has that been automated?
So it hasn't been automated yet, and in the example, right, if you have, let's say, a program that interacts with the network, it's probably unreasonable to assume the analysis is going to be able to interact with, say, a live network service, right? So the kind of one inspiration that I have from, say, doing data flow analysis is you'd build up these, let's say, a realistic model for external ABIs, such as the standard C library. But also, you could just tag based on what you know about specific APIs, instead of having to build an accurate, let's say, a true implementation of these external APIs. You could just develop, say, a system that allows an analyst to mark individual functions as simple stubs, where you provide, let's say, a return value that supports normal execution, right? To build off a simple network program, you could just stub out portions of the socket API such that they don't simply do anything. They just always say return the proper status code that enables a program to continue to operate normally. So at the moment, that's not fully automated, but the vision kind of is to support this tagging that enables stubs to be potentially generated automatically.
Okay, question from Bahira asking, do you recommend MRM for particular services? How sensitive is MRM to false positives and adaptive to different benign events?
So I would say that at present, the MRM would probably be best suited for workloads where you can generate a strong an accurate security policy from the binary, where you have the most confidence that the policy would be representative of all potential executions, right? And and where you would be very concerned about any potential intrusion, right? So if you have those two things, the significant concern for the sensitive workload, and two, the workload itself is implemented in such a way that our analysis produces a very accurate model, that would probably be at the moment the best possible service. If the service is difficult to model, where lots of input is coming in that makes the analysis unable to determine, let's say, the arguments to particular system calls, then you may lead to false positives. But if we admit the kind of maybe a more relaxed security policy where you can designate at this particular point in the program, this is user input, we wouldn't necessarily develop a policy that would be overly precise, but we could still restrict the activity to specific system calls, right? We just probably couldn't enforce the specific inputs over those system calls.
Thank you for covering all that. We're coming up on our break time here, so maybe just final thoughts from you, or where do you see this work going, or maybe what's next from you after your PhD work here? We'll let you have the final wrap here.
Well, I'd be really excited to continue working on this, because this is a really interesting endeavor. Like building security policies that are effective is a really labor-intensive task, but building off the work that's been done at CMU over the last decade, it seems really possible where you could envision a workflow that allows analysts to kind of automatically develop security policies for the way people are developing systems now as large communicating microservices. And that just seems like an incredibly useful service to have without having to pay analysts or like rely on customers to keep their policies up to date as new features are developed and shipped. And I'd like to just say thank you for having me. It was my first FlowCon. I had heard about it last year, and it's been a great experience. Thank you.
William, great work. Thank you so much for joining us today.